Today we are going through Hess's Law in this A-level chemistry revision episode. I am Jono from Seneca, and I'm really excited to talk to you today about Hess's Law. It's a really cool little nifty way of indirectly calculating enthalpy changes. So let's dive in. I'm excited. So it's a really useful way of calculating enthalpy changes, and this is because the enthalpy change of a reaction is independent of the pathway. So the enthalpy change of the reaction is the same if the reaction is direct or indirect. So what does that mean? That all sounds a bit whack. Well, Hess's law is useful for obtaining enthalpy changes that aren't directly observable. These are often obscure reactions. With the help of some easy reactions that involve some of these compounds, we can derive the enthalpy changes that we're interested in. This means that any of the following would all have the same enthalpy changes. So A to B to C to D to E, A to C to E, A to E, they would all have the same enthalpy change because all we're doing is we're converting A to E. And it doesn't matter the steps that we take to do that, the enthalpy change will be identical for all of them as long as we start with A and end with E. So, to summarize, Hess's law states that the enthalpy change of a reaction is independent of the pathway. Now, we can use Hess's law to derive Hess's cycles, which helps us with the calculations. We can create cycles using enthalpy changes of formation or combustion. Okay, so we'll have three pathways, and the two enthalpy changes that go from like A to B and then B to C would be the same as the enthalpy change if you go directly from A to C. So that is just demonstrating that different pathways will have the same enthalpy change, and we can just substitute in the values that we know. So the first type of Hess's cycle is those that use enthalpy changes of formation to calculate the overall reaction's enthalpy change. We can set up a cycle with two enthalpy changes of formations to complete the cycle. And to do this, we need to know all of the enthalpy changes of formation for the reactants and products. And at this point, it's good to remember that the enthalpy change of formation for any element is 0. We use a similar method to set up a cycle for enthalpy changes of combustion. And remember that combustion has the product CO2 plus H2O. So that's how we can recognize when it's an enthalpy change of combustion. Okay, so remember with Hess's cycle, let's say we're going from A to C, that enthalpy change would be the same as going from A to B and then B to C. That's how Hess's cycle works. So they allow us to indirectly calculate the enthalpy change of a complex reaction by considering simpler reactions. So let's say that the enthalpy change of X to Y is 10 joules per mole, and the enthalpy change of Y to Z is 30 joules per mole. What would be the enthalpy change of X to Z? So by using Hess's law, we can say the enthalpy change of X to Z is the same as the enthalpy change of X to Y plus the enthalpy change of Y to Z. So all we need to do is substitute those values in. So 10 plus 30 would give us 40 joules per mole. Simple as that. So that brings us to the end of this episode about Hess's law. Hope that was a useful conceptual run through of it. You might want to practice some questions and maybe do the Seneca online unit to help consolidate this. But hope you're feeling confident about it, and I look forward to joining you on the next episode.